And we've got a good bit of stuff to do, but it's totally doable. And I think we're gonna work through it without a problem. We're gonna be good. Um, we've got at least three poll questions today. Um, and we are going to be talking. We got two poll questions on the first block of material, and then at least one on the next one. But where we are going to start is kind of at the middle point of our last PowerPoint. That last PowerPoint or that last PDF, whatever file you open, is 1310 day three. The first slide that I want you to be pulling up, it has density of liquids on it. Because if you remember what we were kind of wrapping up with last time was a kind of investigation, a question of like taking different measurements. And so today we're going to be looking at some of those different measurements and combining them. So density of liquids is where we're going to kick things off. This is slide number 19 on that day three PowerPoint. We're going to work through this, and then we're going to go on and we're going to talk about what what does an atom consist of. Let me do one last thing so that my space is a little bit more functional for me, and we're good to go. All right, so density of liquids. Here we go. This right here shows I mean, if I were to guess the volume, it's probably about a shot glass. So a couple of ounces of different liquids. Now, if you look at those different liquids, their names are over here on the left-hand side. We've got motor oil at the top, honey at the bottom. Then we've got vegetable oil, hand soap, milk, corn syrup. Now, I want you guys to tell me, and I'm going to go ahead and label them. Um, I'm going to go Drake style and start at the bottom. B, C, D, E, F. Um, what I want you guys to know, and actually, I'm 42. I know I don't look a day over 41, but I am. I need to know, is Drake still culturally relevant? Give me a one in the chat if he is, or a zero if who is Drake is your response. Okay. Okay, good. Um, I saw one person say one IGGGG. I think that means one, I guess. Sidebar, I'm from College Station. That's where I grew up and home of Texas A&M. And his car was spotted in College Station a couple of weeks ago. It was a really big deal. It made the news, which is really kind of crazy. Not that he was spotted in College Station, but just the fact that somebody's car would be like, oh, wow, this guy was driving around town or was being driven around town. But at any rate, thank you very much for your responses on whether or not Drake is popular and culturally relevant anymore. I appreciate that. That's very helpful for me. Okay, so now what I want you to do is look at this, and I want you to give me the letter that corresponds to the most dense solution. We've got honey, corn syrup, milk, hand soap, vegetable oil, and motor oil. I'm seeing lots of A's for honey. You're absolutely right. So now what I want you to do is switch and tell me what's the least dense solution here. Perfect. I'm happy that everyone picked the bookends of A and F and nobody was like C. Um, Now, if I had a solution that was more dense than honey, what would happen? Something more dense than honey, what it would do if I dropped it in here, it would go to the bottom. It would go under. Yeah, absolutely. If it could, it would basically displace all that honey. Now, these are all liquids, and there's a couple of things that are important to know. And this term that I'm going to share is miscible, miscible, versus immiscible. I remember whenever I first learned those words, it was in organic chemistry. Um, And I remember I was like, oh, clearly that's a misspelling. And what it should read is mixable or immixable. And no, it's not a typo, but effectively that is kind of true. If something is missable, or if two solutions, let me rephrase that. If two solutions are missable, they will mix well. And thinking about liquids, let's say that you got rubbing alcohol and added it to water. And you had 1 part water, 1 part rubbing alcohol. You mix them together. That would be a miscible solution because they would mix all together. They would be a homogeneous solution. Meanwhile, if you got, say, motor oil and water, they would be immiscible. They would not mix well together. And that would, at best, it would be heterogeneous. It would not mix well, so they wouldn't really make one consistent or one coherent thing. So this is an important thing. These two miscible versus immiscible is important to know because if you added something that was completely miscible with honey, well, then it would just kind of mix in with honey, provided that it has the same density. Now, what I really want you to take away from this right here, though, is I want you to take away the principle of most dense goes to the bottom, least dense floats. Effectively, I mean, it floats on top of it, goes to the surface of the more dense substance. Now, density is something that I think that you guys understand as a concept, and you probably understand it numerically. Maybe you haven't thought about it though. What we have is a calculation that we can use to determine and quantify the density of something. Now, this number right here, the density of water is 1 gram per milliliter. I want you to remember that. I want you to use that as a reference point. Now, honey, for example, has anyone ever added honey to tea? And we'll go ahead and consider tea to be water. Add a Y or an N to the chat if you have added honey to tea. Okay, seeing lots of yeses. Now, would you say that honey is M more dense or L less dense than water based on having done that? Spot on. You're absolutely right. It is more dense than water because when you add honey to tea, it goes straight to the bottom of the mug or whatever you're drinking the tea from. Now, an ice cube is an ice cube more or less dense than water? Add an M for more or an L for less. An ice cube is less dense because what does an ice cube do when you add it to water? It floats, goes up to the top. Great job. Now, the density calculation, D equals M over V. This is what's known as a two-dimensional unit. Two-dimensional because it's accounting for two different measurements. It's accounting for the mass of something as well as the volume that that thing occupies. So, one thing that I always think about is if you were to construct a brick, a masonry brick, a clay brick that's going to be used for building a house, well, you have a shape for that brick. Therefore, it has a volume, it occupies space. That brick also has a mass. Now, if you made the exact same thing, but out of styrofoam, well, is the volume going to be the same? Yes, it is. Is the mass going to be different? Yes. The mass is going to be different, and that is what is going to cause the density to be different. So, if you're comparing objects, two different objects, A and B, if the volume, let me go ahead and change that, vol are equal, but A is heavier, then A is more dense. If you understand that, then you understand the concept of how to like construct this formula right here. Now we will be doing some calculations, which your homework, which will be posted a little bit later today, as well as the quiz that will be posted later today, will ask you questions about this sort of thing. Now, I'll bring this back up later on, but your quiz is going to be open note. So you can use whatever resources, with the exception of Google or any sort of like you can look back through your PowerPoints, um, but I don't want you to use any sort of like web search or any sort of AI tool to help you with the quiz. I want you to do the work and answer the questions. So your notes, feel free. The PowerPoints that I give you, feel free. I don't think that you should need much more than that. But are the quizzes the assignments we do on paper? No, they are not. Thank you for asking that question. The quizzes are going to be posted. It will appear as a quiz in Canvas. I'll send you the link for it as well. Um, and the assignments that you do on paper, then we'll do that as well. But that has no time frame on it. The quizzes have a 20-minute time frame, and I'll adjust that for folks who have any sort of accommodations. But that's what we got. I'll go into the quizzes a little bit more later on today, and I'll tell you when they're going to be posted and everything. They'll be posted around 2 p.m. today, and they'll be up until Sunday at 11:59 p.m. Okay, so with that in mind, we've got ways to measure densities of liquids. Now, one of the things that's important to know, and actually, is if we compare ethanol and water. Ethanol has a density of 0.79 grams per milliliter. Water has a density of 1 gram per milliliter. Now, does anyone remember earlier this semester I talked about 1 milliliter is equal to 1. I'm going to leave a blank there. Does anyone remember the unit that I had? And I'll give you a little bit of a hint. It starts with a C. Victor, yes, spot on. Wonderful. Great job. Okay. So 1 cc, let me go ahead and say, is equal to 1 cm cubed. So what I really think is important to be able to do is to visualize a cube that is 1 centimeter on each side. Can you give me a one in the chat if you follow that, if you can visualize that? A zero if you're like, I'm having trouble with that. Now, I haven't seen anyone put a zero, but find something around your desk. I got a piece of paper right here. If I had a ruler, I'd be able to rip it and I'd be able to say, okay, well, here's one side that's 1 centimeter by 1 centimeter. I gotta say, that's pretty close to 1 centimeter, I think. Then I'm gonna get another side and I'm gonna, make a point of these two pieces of paper. And I'm sorry, really all that you're seeing is my fat fingers showing you this. But what I want you to see is like, okay, I could imagine if you had a dice or a die that was 1 centimeter by 1 centimeter by 1 centimeter. Again, I think I didn't see too many people say, no, I don't follow that. But at any rate, that's what I want you to do as kind of an exercise. So let's say that we had a, a cube that was made up of water. And I know you might be thinking, well, it's a liquid. How are we going to have a cube of that? Well, one, let's just play with it in your head. Two, well, maybe it's like 0 degrees out. It's an ice cube. Done. Okay. So we've got a cube made up of water and a cube made up of ethanol. Ethanol can freeze. It's a liquid and it can become a solid. That's a physical change. I'm going to write ETOH. That's shorthand notation for ethanol. I'm going to say A and B. When you put block or cube A onto this scale right here, and then you remove it and you put cube B onto this digital balance or this scale right here, which one will show a larger number, A or B, when you record the mass of them? Answers are rolling in. Great. Absolutely right. Great job. A. A will read 1.000 grams. Now, could anyone add to the chat what will be the reading when you put cube B onto this digital balance? What's the mass of cube B? Woo! You're absolutely right. 0.79 grams. Understanding that is maybe one of the most important things about understanding density and thinking about a solid. As soon as you see a density measurement, whether it is the density for mercury, Hg. Mercury has a density of 13.9 grams per milliliter. When I see that number, I immediately convert it to 13.9 grams per cm cubed. Because whenever I do that, then I can say, okay, well, I've got my cube of mercury. Okay, what shows up on the digital balance whenever I put this 1 cubic centimeter cube onto the digital balance? Well, 13.9. So with that in mind, I'd like you to tell me, let's say that I've got a glass of water or a beaker of water, whatever, and I take B and drop it into there. So I've got liquid water and I've got this cube of ethanol. What is B going to do? Tell me, is it going to S sink or is it going to F float? Add it to the chat. Wonderful. Wonderful. It is going to float. I just got a private message from someone. No, you're not absent if you're late or anything like that. We haven't even done a poll question yet, so you're good. Okay, now what if I took this mercury cube, this one that's 13.9? Is that going to S sink or is it going to float? F. Done. Perfect. It is going to sink. The cube of mercury with a density of 13.9 is much more dense than water. So it's going to sink in that glass of water. Okay, you guys are doing a great job, and I'm very happy to see that. Now what we're going to do is we're going to look a little bit more at the density of solids. And this is where we're going to see our first poll question. So everybody get ready. I'm going to bring that poll question up right now. I'll leave it up for a minute or so. This poll question is, which sample of copper, these are both copper, which is more dense? Is it A, B, or C? They're both copper. They're both copper. One looks like it's a sheet, and one is a cube. Heck, this cube might even be 1 centimeter by 1 centimeter by 1 centimeter. Okay, and give about 10 more seconds. If you're unable to see your poll question, if you're on the app, my understanding, or there's a tab that says menu or more, click that, and that will bring up polls. We're going to have another poll question in just a minute. Okay, I'm going to go ahead and end the poll and share the results. If you weren't able to answer that, get ready for the next one, whenever that pops up. Okay, we're sharing the results. The most popular answer was B. Second was C, neither of them, or A is in third place. Now I'm going to stop the share. Um, both of these, this is really tricky because personally, whenever I see this, I think about like taking a sheet of paper and setting it on the surface of water. And I can just visualize it kind of floating around. I can just see it floating there. Whereas this, I look at it and I'm like, well, I just set that in and it's going to sink right to the bottom. Well, I'll tell you this. Copper is more dense than water. Okay, so you would expect copper to sink. And that's actually the correct answer to this poll question. Which copper is more dense? The important part about this is that they are both the same material. So their density is the same. Now, this term right here, intensive property, well, think about an intensive property as being like a subset of physical property. A physical property is something that's descriptive about a substance. So density is a physical property. In addition to that, density is an intensive property. So what that means is that if you have, let's go back to our 1 centimeter. Well, heck, I'm not going to draw it. We've got our 1 centimeter by 1 centimeter by 1 centimeter cube. Okay. If the density of copper is like 6.5 grams per ml, that means that this cube right here that I just put an X on has a mass of 6.5 grams. Now, what if we had a cube that was 1,000 times as large as this? Is it going to weigh more? Absolutely. The larger cube is going to have a greater mass, but the density of it is going to be the exact same. If our volume, if we increase the volume of this cube 1000x or 100, yeah, 1000x. Okay, give me a 1 in the chat if you follow. We're increasing the volume of this cube 1000x. Now what I want you to do is tell me, give me a y or an n. Will the mass increase? A y or an n? Yeah. Okay. So it seems like everyone understands that we're increasing the volume of this cube. The mass of this cube will increase. Could anyone tell me how much will the mass increase? 1000x. You are absolutely correct. So if we increase the volume 1000x, the mass will increase 1000x. So what that effectively means is let's take this number, or let's take these numbers. 6.5 grams times 1000, and then 1 milliliter times 1000. Would everyone agree that this and this will cancel out? Add a y or an n if you follow that those will cancel out. So we are back at the point where our density effectively doesn't change. So that's an intensive property. No matter how much of that substance you have, the density will not change. That's what an intensive property is. Okay. Now I'm going to go on here. I'm going to show you this. We're going to go to this little exercise right here. So I'm going to grab that link, switch my share in just a second. Dang it, that one. What happened? This link used to be freely available. Let me see if I can. It used to be one. Okay, I think there we go. Well, Well, we'll go to this other one a little bit later. Okay. So we can we can measure the volume of something in a process known as displacement. So just imagine for a moment, I'll use this example. I have a 6 month old child. His name is Hank. He's adorable. He's wonderful. Now let's say that let's compare Hank, one of my kids, to a cube. Bear with me or go with me on this. Um, how could I figure out the mass or the weight of Hank? I can put him on a digital balance, 1 or 0 if you follow that. Obviously, it'd have to be like a scale larger than a digital balance. Okay. Now, I could do the same thing with the cube. So figuring out the mass of the cube is kind of easy. So I'm going to put a check mark on that. My destination, my goal here is to figure out the volume of these two. Okay. Now, could anyone give me a formula with how I could figure out, add it to the chat, what could I do to figure out the volume of a cube? Perfect, Terry. LWH. Length times width times height. So with that, could I apply that same equation to easily, I'll say easily, figure out the volume of my son Hank? Not really. That'd be a little bit trickier. So rather than doing that, we can do something like displacement. And to visualize that, Hank has a bathtub. And if I filled this bathtub all the way up to the brim and I put Hank into the bathtub, what's going to happen to the water? Perfect. It's going to spill out. Thank you. I love the dramatic overflow. I like to imagine that you were using text to talk there, or one of your classmates was using text to talk and yield, and in all caps said overflow. Yeah, it displaced. So if I wanted to figure out the volume of Hank, what I could do is capture all of the water that overflowed. Because when Hank gets into this bathtub and water spills out, basically that water volume is the exact same as the volume that is Hank or Hank's volume. Now, that's known as Archimedes' principle. What we're going to do instead is use measuring density by displacement. So if I got this iron ball right here, I'm put an X on this iron ball, and I put it onto this digital balance, I'd be able to figure out the mass. And let's say, just for the heck of it, the mass is let's say 13.96 grams. Okay, cool. To calculate the density, I need mass over volume. Well, that's a ball. Measuring the volume, it's kind of tricky, but if I put it in here, I know the initial volume of the water in here. It's at 200 milliliters. Let's say that when I put that iron ball in, it sinks, and the new water level goes up to 206.2 milliliters. Could anyone tell me in the chat what is the volume of that iron ball? Done. 6.2. So now, if I wanted to figure out the density of this iron ball, let's say 13.6 divided by 6.2. And that would be something like, 2.0 5. I don't know. I just threw that number together. Could you give me a 1 in the chat if you follow that, a 0 in the chat if that doesn't make any sense? Okay. Now, next up, we've got a little bit of an issue, and this is a Zoom poll where, unfortunately, because this link was dead, I swear it worked about an hour ago. Um, what I want everyone to do is whenever I bring this poll question up, everyone answer A. Go. And if everyone answers A, hmm, I don't know what the terms are. Not going to have any terms. Just everyone answer A real quick. Oh, so close. So close. Oh, so close. One person answered C, one person answered D. They didn't hear me, I guess. I know, I know. Oh, another person answered C. Another person answered D. Now we've got just this revolution. Okay, I'm gonna go ahead and stop the poll so that the revolution is stifled. But the point of this is that somebody said they are trolling. Totally. Um, this is important because if I had a mystery solid, let's say that I did that exact same thing and I put in a block or a cube that was 5.4 grams and occupy and had a volume. So I have this mystery solid that has a mass of 5.4 grams and a volume of 2 milliliters. What would it be? Well, it would be A, aluminum, because I can take D equals M over V, my mass, 5.4 grams, over 2.0 milliliters. 5.4 divided by 2 is 2.7 grams per milliliter. Now, think about that as, okay, well, if if I found some random object and I determined the density was 10.5 grams, do I have an idea of what that object could be? Yeah, it's probably silver. Or let me rephrase that. That is one piece of evidence that suggests that, hey, I found some silver. Well, what else do I know about silver? One other physical property that I know about silver is that it's shiny. So if I've got two pieces of data, the density and the shininess, do I have an idea that, hey, this is silver? Yeah. So when you're presented with an object of a certain mass and a certain volume, and you can determine the density, if you find something that has a mass or a density of 8.9 grams per milliliter, chances are strong that that is nickel. Physical properties can help you identify something. Can you give me a 1 if that makes sense, or a 0 if, wait, I don't get that. Okay, awesome. So it's one piece of evidence. It's one data point that tells you this is what this is. Okay, now we can measure the density of something to identify a metal. For example, right here, we measure the mass of this object, 29.5. I'm gonna go ahead and get my phone ready to be my calculator. 29.5 grams. Okay. Now, whenever I look over here, I've got my initial volume. That's about 35 milliliters. My object is not in there. I throw it in here. And now my new volume is approximately 40 milliliters. Okay. So the volume of this object is roughly 5 mils. So I'm going to take 29.5 divided by 5, and I get 5.9. Now, if I had evidence that this thing was zinc or aluminum, if I had other pieces of evidence that said that this was zinc or aluminum, I'd be like, well, chances are that it's zinc with maybe some sort of contamination or some sort of imperfection or something like that. It's, or what I could say is, well, maybe this is a mixture of aluminum and zinc, but mostly zinc. Okay. Now we are going to jump ahead a couple slides because I feel like we've got that point. Now, this is the other thing that I wanted to share with you. This is a little activity, a little exercise that you can do to help kind of visualize and conceptualize um, density. Just a second. Okay, there we go. There. Okay. So we've got density, and what we can do is compare different objects. Okay, so I'm going to go with this. What is something that you notice about these objects on the left hand and the right hand side? A, B, C, and D. What do you notice about their mass? Tell me about their masses. They're all the exact same. Now, what I'd like you to do is give me a prediction. A, B, C, or D. Which one of them do you think is going to be the most dense? Got to vote for D. In particular because, well, it's the smallest. They all have the exact same mass, but D has the greatest mass and the smallest volume. Now, we can throw block D in. Lo and behold, it sinks. What is the volume of that block? 1.25 liters. Because whenever we drop it in, it goes up to 1.25. Okay. Block C. Okay. 2.5. So that's 2 times as voluminous as block D, but the mass is the exact same. Now, I'm going to go over to block B now. Block B. Is the volume 5 liters? Do you think it's more? Do you think it's less than 5 liters? Tell me give me M if you think the volume is more than 5 liters, L if you think that it's less, or E for exactly 5 liters. Okay. Most everyone's chiming in with M. I see a couple E's and a couple L's, and this is the tricky part about this. This block floats. Is it displacing all of the volume of it? No, it's not. It's displacing about half of it. So in this demonstration, if we really want to get the volume of it, here's what we got to do. We've got to click and hold it and drag it down because that is going to show us the actual volume of this block or actual volume of this cube. So what is the actual volume of this cube? Add it to the chat. 10. Now, what I'm going to do here is I'm going to add this little activity to the chat so that if you want to, you can kind of tinker around with it. But then I'm going to go back to sharing my screen because I feel like we're doing pretty well on density. So one of the things that I want you guys to kind of anticipate for your quiz, your exams, those sorts of things, is I want you to be able to do that calculation where I will give you a volume or I will give you a mass. I'll say this object has a mass of this whenever it's added to Graduated cylinder, it completely sinks. The initial volume is this, the final volume is this. What is the density of this object? And then also be able to identify it. Say, well, based on this information, this is the object. Okay, so I feel like we've gotten that. So our baseline is D equals M over V. Now, these two configurations are really just rearrangements of that same equation. So what I want you to be able to do is say, if you have 50 milliliters of an object that with a density of 6.4 grams per mil, what's the mass of that object? Well, then you would say density 6.4, volume 50. 6.4 times 50 would be about 320 grams. Now, considering all that, I think that if you can do this sort of rearrangement, which you're going to see questions like that on your homework, so that will give you good practice. Um, which again, the homework and the quiz are going to be up at about 2 or 3 this afternoon. And I'll send you a link letting you guys know, hey, they're up. Here you go. Here's your links. Um, Other than that, though, that's what I wanted to talk about with respect to density. Now we are going to change gears. I'm going to go ahead and end this slideshow. I'm going to stop my share for a second. We got more to talk about today. And my slideshow, do I want to keep my annotations? I do want to keep them. Keep. Then we've got another PowerPoint. Another PowerPoint, which is somewhere. There it is, day 4. So now I'm opening up the day 4 PowerPoint. The first slide that you should see in this slide deck is atomic structure, electrons in atoms. I've taught this class a good number of times, and this is the sequence that I like to do because whenever I think about an atom, um, first of all, what is an atom? An atom is the thing that makes up everything. What's the triangle? The the triangle. I think that was just some of my markings that appeared on the screen. Um, so an atom is the basic unit that builds up everything. Um, and the way that I always think about a molecule is I think about how do I construct this thing? And so what we're going to talk about today is we're going to introduce the different models of an atom. Okay, no, like there is a triangle you can use for DMV. Yes, there is. So that is one thing that I can go ahead and send that out. Um, there's a way that people like to, let me do a quick Google search. Density equation triangle. I'm sorry, let me get this real quick. Um, yeah, that's a good one. Oh, there we go. Some people like to use this right here, and I'm going to go ahead and add a link to it. Sorry, everyone. This is just one other way that you can look at the density equation. Um, okay, now I'm back. Um, so I always like to construct things. Like, what is my base unit? What am I going to build it into? And that's the way that I always like to talk about and think about an atom. That's the way that I like to talk about and think about a molecule. And that's the way that I like to talk and think about really big things. Um, if you can build from there, you're going to be in good shape because my background is in biochemistry. And so it's helpful for me to think like, okay, I can see a corn kernel, but what is that made from? And could you get it down to atoms? Yeah, absolutely. And that's, to me, that's a really helpful way to look at it. So, first and foremost, the model of an atom. We've got on the left-hand side a very old rudimentary idea of what an atom is. Then we got this one right here. This is known as the plum pudding model. And for a while, this was the emerging or the popular model for what an atom looked like. There was this idea that, hey, an atom is like a ball with a positive charge, and then there's a bunch of electrons all over the place. The idea is, and add a one to the chat if you have ever had plum pudding, or a two if you have never had plum pudding. One if you have, two if you've never. Yeah, I see lots of twos. Same. If you've had plum pudding, cool. I have never had plum pudding. If you are going to go with a three and say, I think I have, but I'm not sure, go for it. I've never had plum pudding, so I can only kind of speculate that I've decided that it's kind of like what is it? Like a blueberry cobbler or something like that. Um, the blueberries being these negatively charged things. So there's this idea that, well, you've got this ball that has an overall positive charge, but then it's got a bunch of negatives floating around there. Okay. So that's kind of an intermediary theory of what an atom looked like. And then over time, it evolved. And people did some experimentation. So there was experimentation that took us from this one to this one, and then experimentation that took us from this one to this one. Tests where people were like, I wonder if there's any sort of charge on this ball. Oh yeah, lo and behold, there's positive and negative charges on it. Oh, cool. It's got some like electronic potential. It can conduct electricity. Ooh, fascinating. And then there was a guy named Ernest Rutherford, E. Rutherford, who he said, "Oh, as it turns out, this plum pudding model, no good." Or maybe not no good. He was like, "We can do better than that." And what he did was he cooked up this idea, and since then it's been evolved a little bit more that basically the most space of an atom, or the most volume, most of the volume of an atom is where negatively charged things known as electrons are. And then at the very, very small center of it, there's a nucleus. And that nucleus consists of different things. That nucleus is composed of only two things. In the nucleus, there are protons, which are positively charged, and neutrons that have no charge or zero charge. So essentially, and add to the chat Y or an N if you have ever heard the term subatomic particle. Okay, so lots of people have heard a subatomic particle. Let's break that term down. Subatomic. Sub meaning, well, you could look at it as below or underneath. Atomic. Okay, so we're lower than atomic. Lower. And I'm going to rephrase that. Rather than lower than atomic, I'm going to say lower than atom. So something lower than the atom level or the atomic level is subatomic. So neutrons, protons, and electrons are all things that, if you look at an atom, they are lower than or smaller than the atom itself. So when you think about an atom, yeah, an atom is used, or atoms are used to build everything, but electrons, protons, and neutrons are used to build atoms. Could you give me a one or a two? A one if you understand, okay, we use electrons and neutrons and protons to build up an atom. And two if you're like, what? So it's helpful for me to sometimes think about it in terms of like a Lego. Okay, well, these are electrons, protons, and neutrons are the individual Lego pieces. And we can put them together to make an atom. And I'll just simplify an atom and say a little ball. So I use these protons, neutrons, and electrons to assemble them, or to assemble an atom. So that's where this subatomic particle comes from. Now, the question is, or the question was, with this plum pudding model. Like Ernest Rutherford, like I said, he used an experiment to ultimately say that this model was no good. Now, what he found was that, or basically the important takeaway of disproving the plum pudding model is that an atom puts protons and neutrons in the middle, or in its middle. And this middle is known as the nucleus. Okay, so if you're thinking, what do I need to know about this plum pudding model? That's what you need to know. The nucleus is where your protons and neutrons are found. And then to follow that up, well, what that means is that your nucleus has two particles with, well, is made up of two particles, or two types of particles. They are protons, which are positively charged, and neutrons, which have no charge whatsoever. Okay, so let's say that a nucleus had one proton and one neutron. Would everyone agree that one proton and one neutron has one positive charge and one zero charge? Add a Y if you would agree with that statement. I'm not going to give you the option to disagree with that one because that one's just, we're going with that. Now, with that in mind, tell me in the chat, and you can use the symbol or use a number, what is the overall charge of this nucleus? Is it negative? Is it positive? Is it zero? I see lots of positives. You're absolutely right. Because think about it in terms of numbers almost. What is the answer? If you add positive 1 to 0, that's going to be positive 1. If you add positive 1 to negative 1, what is the answer to that? I know I'm switching gears here a little bit, but what is positive 1 plus negative 1? 0. So if you have something that has no charge or is neutral, and you add that to something that's positive, well, that combination is positive. Okay? So a neutral particle cannot kind of cancel out a positive particle. Okay. Now, these different subatomic particles, protons, neutrons, and electrons, I want you to know where they are. I want you to know their mass, their charge, and a couple of other things about them. Protons, positively charged. Neutrons, neutral. Their location, protons and neutrons, are found in the nucleus. And their mass is approximately 1 AMU, or AMU stands for atomic mass unit. Okay, so in comparison to a proton and neutron, an electron has 0 AMU. Now, thinking about that, let's say I had 30 protons, and to that I added 25 neutrons. And to that I added 40 electrons. What is the mass? What is the overall mass of this? Okay. And my units for mass are going to be an AMU. Well, 30 protons has a mass of approximately 30 AMU. Plus, Kelly, you're absolutely right. 25 AMU. Plus, well, electrons. Each electron basically has 0 AMU. So Kelly's absolutely right. That combination is going to be 55 AMU. Okay, so that accounts for this mass calculation. Actually, let me redo that. I'm going to put that as a mass calculation. Now, to follow that up, I want to do a charge calculation of this exact same combination of subatomic particles. Your charge is going to be positive or negative. It can be +5, it could be -4. What am I going to get? Well, 30 protons is 30 positives. Add that to 25 neutrons or 25 zeros. And Kelly, you got it again. 40 negatives is going to end up being essentially 30 positive plus 40 negative, or -40, is going to give me a charge of -10. Could everyone give me a 1 if they follow that, or a 2 if they'd like me to redo a charge calculation? Okay. So now let's do another charge calculation, and then I'll ask about a mass calculation. I'm going to make an atom. Let's say an atom is always going to be the amount of protons present. I got a private message question. Is your charge always going to be the amount of protons present? Your positive charge is going to be the number of protons present, but the overall charge is going to account for the protons and the electrons. So let's say that I've got an atom that consists of 12 protons, 9 electrons, and 13 neutrons. Okay, so this is what my atom explains. Can you explain again why the 40 electrons is 0 AMU, please? Absolutely. Because when we look at our mass column right here, this tells us the mass of our proton. So proton mass is 1 AMU. Neutron mass is 1 AMU. And then electron mass is 0 AMU. Okay. Now, looking at this charge calculation. So this new atom that I just put together, 12 protons, 9 electrons, 13 neutrons. What I first want to do is look at my charge. 12 protons, 12 plus, because each proton, each one of those protons has a charge of +1. So I'm going to put a check mark by those. Then I've got 9 electrons. Each electron has a charge of -1. So that's plus -9. I'm going to put a check mark there. Last but not least, well, I just want to account for this because I'm looking at everything. What charge does each neutron bring around? 0. So I'm doing +12 plus -9 plus 0. My overall charge here is, add it to the chat whenever anyone's got it, +3. Great job. What I have to do is balance my protons and my electrons. Figure out, okay, well, I've got these 12 positive charges and then these 9 effectively canceling out negative charges. Now, what I'd like to do is the exact same atom, but a mass calculation. Okay, so 12 protons. Now I'm going to go over here. And I'm looking at this mass column. What's the mass of one proton? That is 1 AMU. So 12 protons is 12 AMU. Plus 9 electrons. Ooh, an electron has a mass of basically 0 AMU. So I'm going to say +0. Just the last subatomic particle that I need to think about is my 13 neutrons. So I'm going to add +13 because each neutron has 1 AMU as its mass, +13 AMU. And I get 13 plus 12 is 25 AMU. Okay. Now, could everyone add a 1 in the chat if they follow all that? Okay. So these are just definitions for each one of these subatomic particles. And these are definitions that you need to know. Now, the last thing relates more to the periodic table, which we will get to, and we'll revisit this. I want this here, though, so whenever we revisit it, or whenever we get to the periodic table, you can reference back to this. You can come back to this. But in the interest of time, well, actually, not really in the interest of time, but now what I'm going to do is go ahead and launch a poll. Which statement is true? We've got option A, and nobody should be entering anything into the chat right now. The nucleus of an atom contains neutrons and electrons. B, the atomic number of an element is equal to the number of protons in one atom. C, the mass number of an atom is the number of protons in the nucleus plus the number of electrons outside. And D, the number of electrons outside the nucleus is the same as the number of neutrons in the nucleus. Okay, I'm going to launch this, and what I want you to do is kind of pause and think about this for a moment. Because what I'm going to do, and if you feel confident in your answer, go for it. But what I'm going to do is go back. Okay, so A, the nucleus of an atom contains neutrons and electrons. Well, has anyone done an experiment to investigate that? Yeah. Ernest Rutherford found that electrons were kind of everywhere, making up this electron cloud. The nucleus of an atom contains neutrons and electrons. Well, neutrons are in a nucleus, but electrons are kind of everywhere. So A is out. Now, D, the number of electrons outside the nucleus is the same as the number of neutrons in the nucleus. Oh boy. Well, for that, we should look over here. We've got the number of electrons, this last column, or this last cell, the number of electrons is equal to the number of protons for a neutral atom. Then let's look at this one. The number of neutrons is equal to the mass number minus protons, or this one right here, the number of protons is equal to the atomic number, which is equal to the identity of an atom. Do any of those relate electrons and neutrons to one another? No. So D is out. What we're really down to is B and C. B says the atomic number of an element is the number of protons in one atom. Okay, so let's take the back end of this question, or this answer option, and say the number of protons. Okay, now let's go back and look at these different options. Our definition, or our row right here where we're talking about protons, ends with the number of protons is equal to the atomic number. So that's what chemists use. They say, how many protons does this atom have? Based on that atom, we identify an element. So what I'm getting at there is, if you have an atom with 12 protons, then that atom is element, I'm just going to use a filler, element X. Now, if somebody comes along and they find element X, how many protons does the nucleus of element X have, or that atom have? It has 12. That's a definition there. Okay, so the atomic number of an element is the number of protons in one atom. That's spot on. That's absolutely true. And that's the popular answer. That was popular answer before I said that. Now let's look at this one. The mass number of an atom is the number of protons. Okay, so the mass of one atom is the number of protons in the nucleus plus the number of electrons outside. Wait a minute. before we even look back at this, the mass number, answer in the chat, Y or N. Do electrons have mass effectively? No, their mass is 0 AMU. So this answer option, even without looking at the definition, logically that doesn't make any sense. Now, our mass number is equal to the number of protons plus neutrons. So if ever you're asked, like, mass of atom is equal to number of protons plus number of neutrons. Okay, so B is the correct answer here. Now I'm going to go ahead and end the poll. 88% of the class answered B. You had like 4 minutes to answer that one, so I think we're good on making a contribution there. Because again, I'm not grading, or I'm not looking for did you get the answer right? I'm just looking for did you participate in this one? Okay, so now what I want to introduce you to is this idea right here. So an isotope. Has anyone ever heard of, add a one to the chat if you've heard of this, two if you've never heard of this. Isotopes or radiocarbon dating is what I was going to ask about. Radiocarbon dating is the way that, if you become an archaeologist and you find some sort of mummy, I don't know if that's the correct term, but if you find some artifact and you're like, how old is this artifact? Well, the way that it's determined is based on any sort of the amount of a particular carbon isotope that's present. Okay, so here's what I want you to recognize. This is an atom of hydrogen. That's the nucleus. I'm going to put a box around the whole thing. Add to the chat in this box right here, how many neutrons do you see in the nucleus? 0. Okay. How many protons do you see in the nucleus? 1. Okay. Now, tell me in the chat, first tell me the charge, and then put a semicolon, and tell me the mass. What is the charge of that thing that I've got a box around there? Perfect. The charge is +1, and the mass is 1. Great job. Okay. Now, this proton, this single proton here, compare this atom right here to this atom right here and this atom right here. All three of these have 1 proton. So all three of these are hydrogen atoms. Because our number of protons tells us this is indeed hydrogen. Now, if we look at this one in the middle, I'm going to put a box around. I want you to do the same thing. Tell me the charge. Or actually, I'm sorry, I made a mistake earlier. I said that the charge of, well, correct it here. The charge and then the mass. Okay. The nucleus right here has 1 proton, and that's 1 electron. 1 positive and 1 negative. Use that whenever you tell me what is the charge and then the mass of this thing that I've got a box around. Of this atom that I have a box around. And add that to the chat. Remember, 1 electron, 1 proton, a positive charge and a negative charge. They're going to cancel one another out effectively. That was my mistake that I made earlier. I apologize. This right here has a charge of 0. I apologize. And a mass of 1. Okay. So now we're seeing answers of 0 and a mass of 2. Okay. And now the exact same thing for this last one. Charge, mass. 0, 3. Now, what's kind of tricky about this is these are all hydrogens, but they differ a little bit from one another. They differ in their masses. Now, this is important because what does it go back to? Or what's the important takeaway from this? Is the mass number. The atomic mass for each one of these, well, they differ, but the number of protons is fixed. They all have 1 proton, and therefore they are all hydrogen atoms. So if I added 15 more neutrons, I'm still dealing with a hydrogen atom. So long as I never change the number of protons, I'm not changing the identity of the element. So now what I want to ask you is, let's say that I made this atom right here. 1 proton, neutron, 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 neutron. Electron, 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 electron. First, can you tell me the identity of this atom? Add a Y or an N, if you can. Yeah. Next up. So the identity, it's hydrogen. Tell me the mass of this. Accounting for all of those different subatomic particles. 6. 6 AMU. And last but not least, charge. Tell me the charge of this. But I see negative on there, and I like that. But tell me, is it -2? Is it -3? I'm seeing -7. Let's see, 2, 3, 4, 5, 6, 7, 8. I'm seeing -7, and you're absolutely right. There are a total of 8 negative charges, but then there's 1 positive to offset one of those. So that's what makes this a little bit different. Okay. Now, with all of that to say, we have atomic symbols where we include all this information. And what we're going to get to starting on Tuesday is we're going to look at the periodic table. Well, yeah, we'll talk about it a little bit today, and then we'll go back from there. This symbol right here tells us all of the information that we need to know. And we can use this information to kind of visualize this atom. Okay, so we've got an atomic symbol, Li. I always like using Li because it's my favorite Nirvana song, Lithium, and it's kind of simple to draw. Li, if I were to draw this atom, I would have, and I'm going to draw it right here, P, P, P. Because in the lower left-hand corner, I've got this 3. My atomic number, that's the number of protons that this has. Okay. Now, next up is my mass number right here. Well, that's the number of protons and the number of neutrons. Okay, so how many, if I'm going to draw N for my neutrons, how many N's should I draw around these P's? Perfect. 4. 1, 2, 3, 4. Have I drawn everything that I need to draw for my lithium nucleus? This is a little tricky of a question. I'm not intending to throw you off, but for the nucleus, yes. For the atom, no. For the atom, what else do I need to draw? Electrons. Because if you look at this thing right here, if I were to say, hey, there's an atom of lithium, well, I didn't draw any electrons. Does that mean that, well, sorry, let me rephrase that. If I was like, hey, I'm done. Okay, well, then you've drawn a lithium atom with a charge of +3 and a mass of 7. Does ever add a 1 to the chat if you follow how I came up with this is an atom with a +3 charge? Great. Now, based on this right here, tell me the number of electrons that I need to draw or write in. 2. Perfect. And this is the sort of thing that I know that I stumbled over this sort of question, but the way that I always like to do it is I like to say, okay, well, if I added 1 electron, well, this 1 electron kind of negates this proton. So now I'm looking at something with a charge of +2. Well, if I drew another electron in, well, that electron cancels that one out. Okay, so now it has a +1 charge. Okay, so yeah, if I'm looking for a lithium atom with a charge of +1, this is it right here. Could you add a Y or an N to the chat if you follow that? Great. I'm seeing lots of Ys. That's what my grade is for. Now, the periodic table right here has a couple of different numbers. There's 2 main numbers that I want to draw your attention to. The one above the symbol is your atomic number. So let me ask you this. Of this atom right here, known as cobalt, how many protons does cobalt have? 27. Perfect. How many protons does Ga gallium have? Wonderful. Okay. Now, let's say that I found a gallium atom with a mass of 70. How many neutrons does it have? 31 protons. How many neutrons? Somebody privately messaged, yes, 39. 39. Because 70, which is my mass, minus 31, 6, 1, 9, 3. 39. Okay, I'm going to stop there for today. We'll pick this up on this slide. This is slide number 9. We're going to pick up on slide number 9 on Tuesday. I hope you enjoy your weekend. I hope you have a great weekend. I think the Bobcats are playing again this weekend. I mean, it's college football, so it's going on like all the time. And the NFL starts tonight if you're a football fan. I will send an announcement with your quiz and homework info later today. Expect that between 2 and 3. And have a great afternoon. I'm going to go to my office hours in just a second. Got to go to the other link because I offer my office hours for my other class as well. And I'll answer any questions that you have. Other than that, I'll post everything later today, including the marked up slide decks. All right. I'll see y'all.